Here is a question that sounds childish and is not. You are driving and the needle on the speedometer reads 60. What does that mean? The easy answer is that you are covering 60 miles every hour. But you are not going to drive for an hour. You might turn off in 30 seconds. So try again. In the last minute, you covered a mile. Fine, but the needle is telling you something about now, not about the last minute, and you might have sped up and slowed down within it. Shrink the window. In the last second, you moved about 88 feet. In the last hundredth of a second, about 10 inches. Now shrink it all the way. What is your speed at a single instant? At an instant, no time passes. And in no time, you cover no distance. So your speed at this instant is 0 divided by 0, which, as we established in Chapter 7, is the one question in arithmetic that has no answer at all. Not because it is hard, but because it is flawed. Every number satisfies it, so none of them does. And yet the needle says 60. Something is being measured. There is a fact about how fast you are going right now, and the obvious way of computing it self-destructs. That is one of the two problems calculus solves. The other is Archimedes' problem from Chapter 5, finding the exact area enclosed by a curved boundary, which requires slicing a region into infinitely many pieces and adding them up. Infinitely many pieces of no thickness whatsoever, which ought to add up to nothing at all. Both problems had been circled for 2,000 years. Both involve doing arithmetic with quantities that are somehow smaller than any number but not 0. And in the 1660s and 1670s, 2 men in 2 countries solved them, discovered that the 2 problems were secretly one problem, and built from that a machine that would go on to describe the motion of the planets, the flow of heat, the propagation of waves, the shape of a hanging chain, the growth of populations, the behavior of electrical circuits, and very nearly the whole of the physical world. The machine worked flawlessly. It also could not be justified. Every calculation it performed involved a step where a quantity was treated as non-zero, and then, moments later, treated as 0, and no one, for 150 years, could explain what that quantity was. An Irish bishop noticed. His demolition is the most effective piece of criticism in the history of mathematics, and everyone ignored it because the answers kept coming out right. The great insight, and the reason we say Newton and Leibniz invented calculus when so many others found pieces of it, is that the 2 problems are inverses. Think about it with distance and speed. If you know your position at every instant, you can work out your speed at every instant. That is the first problem, and we call it differentiation. And if you know your speed at every instant, you can work out how far you have traveled. That is the second problem, adding up an infinity of tiny displacements, and we call it integration. They undo each other. Differentiate a distance and you get a speed. Integrate that speed and you are back to the distance. It is exactly the relationship between multiplication and division, or between squaring and taking a square root. And once you see it, the entire subject snaps into shape. Because any technique for one problem instantly becomes a technique for the other. That is the fundamental theorem of calculus, and it is what neither Archimedes nor the Caroline mathematicians had. They had beautiful, hard-won results for particular curves. What they lacked was the recognition that finding slopes and finding areas are the same activity run in opposite directions, and therefore that a general method for one is a general method for both. Leibniz found it, characteristically, in a place nobody would look. In Paris, being tutored by the great Dutch physicist Christian Huygens, he was set an exercise about adding up a particular sequence of fractions. He noticed that each term could be written as the difference between 2 others, so that when you added them all up, almost everything canceled and only the n survived. Sums of differences collapse. Differences of sums collapse. The 2 operations undo each other in a simple problem about a list of fractions, with nothing infinite about it anywhere. Then he asked what happens when the steps become infinitely small and the whole subject opened in front of him. Isaac Newton got there first and told almost nobody. He was born on Christmas Day 1642 in a Lincolnshire farmhouse, premature, and so small his mother said later he would have fit in a quart mug. His father was already dead. When he was 3, his mother remarried and left him to be raised by his grandmother, and he seems never to have forgiven her. Among his surviving papers as a list of sins he compiled as a young man, one of which is having threatened to burn the house down with his mother and stepfather in it. He was solitary, suspicious, obsessive, and easily wounded, and those traits are not a colorful aside. They are load-bearing. Nearly everything that went wrong in this chapter follows from Newton's inability to bear criticism or to let go of a slight. He went to Trinity College, Cambridge, in 1661, paying his way by waiting on wealthier students. And in 1665, the plague came, the university closed, and he went home to Woolsthorpe. He was 22, and he stayed for about 18 months, and in that time he worked out the binomial theorem for fractional powers, invented calculus, which he called the method of fluxions, carried out the prism experiments that showed white light is a mixture of colors rather than a pure thing that glass corrupts, and conceived the idea that the force holding the moon in orbit and the force pulling an apple to the ground are the same force, weakening as the square of the distance. He later described those months as the prime of his life for invention, and said he had been more attentive to these things then than at any time since. It is the most productive year and a half any human being has ever had, and he spent it alone in a farmhouse because a disease had closed the schools. The apple is real, incidentally, in a particular sense. It is not a later invention. Newton told the story himself in old age, to at least 2 people who wrote it down, that he was sitting in the garden, saw an apple fall, and began wondering why it always went straight down toward the center of the earth, and whether that pole might extend as far as the moon. What is false is the shape the story has acquired. Nothing hit him on the head, and there was no flash of complete understanding. What he had in the garden was a question, and it took him 20 years, an enormous quantity of mathematics, and considerable prodding by Edmund Halley before it became the theory of universal gravitation. The apple did not deliver an answer. It started a very long argument with himself. Newton's version of calculus was built on motion. He imagined quantities as flowing, a point sliding along a line, generating a length as it goes, and the thing he wanted was the rate of that flow, which he called the fluxion of the flowing quantity. It is a physicist's picture, and it comes naturally to someone who is thinking about planets. Here is the machinery, and I want to show it to you concretely, because you need to see it clearly to feel the force of Berkeley's attack later. Take the simplest interesting curve, the one where the height is the square of the distance across. Ask how fast the height is changing at a given point. Newton's method. Nudge the input by a tiny amount, which he wrote as O. Then the new height is the square of the old input plus O. Multiply that out and you get 3 pieces. The original squared value plus twice the input times O plus O times itself. So the change in height is twice the input times O plus O squared. And the change in input is just O. Now form the ratio, how much the height changed, divided by how much the input changed. Both parts of the top have an O in them, so you can cancel it against the O on the bottom, and you are left with twice the input plus O. And now the final step. Since O is vanishingly small, discard it. The answer is twice the input, which is correct, it is the right answer, verifiable or dozen other ways. And it is the answer every calculus student on Earth still gets today. Look hard at the last 2 steps because there is a crime in there. To cancel the O on the top against the O on the bottom, you had to divide by O. And you can only divide by O if O is not 0. Division by 0 is not permitted. That wall was built in Chapter 7 and it does not move. But then, 1 line later, you threw away the leftover O on the grounds that it is negligible. And a quantity is only negligible in an exact result if it is exactly 0. If O is some genuine tiny number, then the answer is not twice the input. It is twice the input plus a bit, and your result is wrong. So O must be non-zero in line 4 and 0 in line 5. It cannot be both. Something has gone badly wrong, and the answer is right anyway. Gottfried Wilhelm Leibniz was almost Newton's opposite in every respect except capability. Born in Leipzig in 1646, he was a polymath of a kind that has essentially gone extinct: philosopher, diplomat, lawyer, historian, geologist, librarian, engineer, inventor. And in his spare time, one of the great mathematicians of the age. He worked for princes, drafted political schemes, negotiated between Protestant and Catholic churches, designed windmill-driven pumps for silver mines, and wrote something like 15,000 letters to more than 1,000 correspondents. He came to mathematics late. He was in his mid-20s before he studied it seriously, and he came to it in Paris, where he had been sent on a diplomatic errand and stayed for 4 years. Huygens took him in hand and set him to reading, and within 3 years Leibniz had built the calculus. On a manuscript page dated the 29th of October 1675, he wrote a long, elegant, curving letter S. It stood for summa, a sum, the sum of infinitely many slices. It is the integral sign. It is on that page for the first time in history, and it has not changed since. He also chose d for a difference, and wrote the rate of change of one quantity with respect to another as one d thing over another d thing, in the form of a fraction. And this is where Leibniz beat Newton comprehensively, not in discovery but in design. Newton wrote his fluxions as dots over letters. It is compact and it tells you nothing. Leibniz's notation tells you what the thing is. Writing the derivative as a fraction reminds you at every glance that it came from a ratio of two changes, and remarkably, it goes on behaving like a fraction in situations where it has no right to. So that a student who manipulates it as though the pieces were ordinary numbers usually gets the right answer. The integral sign, a stretched S, keeps the idea of summation visible in the symbol. This is the thesis of Part 3, arriving with a vengeance. Good notation is not decoration. It does part of the thinking for you. And bad notation makes you do that thinking again every time. The consequences were severe and lasted a century, and we will come to them. Now the disaster. The timeline is not in serious dispute. Newton developed his method in 1665 to 1666. He did not publish it. He wrote it up in manuscripts that circulated privately among a few English mathematicians. And there it sat, why the silence? Partly temperament, but mostly because in the 1670s, he had published his work on light and color and been publicly criticized, especially by Robert Hooke, and had found the experience so intolerable that he essentially withdrew from scientific publication for years. Newton would rather possess a truth in silence than defend it in company. Leibniz developed his version in 1675, independently from a different starting point, with different notation, and a different underlying picture. He published it in 1684 in a short and famously dense paper in a German journal, followed by the integral 2 years later. So, Newton discovered it first. Leibniz published it first. And in between there were letters. In 1676, through an intermediary, Newton wrote twice to Leibniz, long letters describing some of what he could do, without explaining how. In the second, he wanted to record a key result without giving it away. So he encoded the statement as an anagram. He wrote out the Latin sentence, counted the letters, and printed them as a scrambled list. The idea was that if anyone later claimed the result, he could unscramble it and prove he had known. That single detail tells you everything about the intellectual culture of the moment. It is the world of Chapter 11, of secret methods and public duels, surviving into the age of the Royal Society. Leibniz also visited London in 1676, and during the visit, he saw some of Newton's unpublished material. That fact became the seed of everything that followed. For 20 years, the two men were civil and even complimentary. Newton, in the Principia, acknowledged that Leibniz had a method much like his own. Then, around 1699, a Swiss admirer of Newton's suggested in print that Leibniz had taken the calculus from Newton. In 1708, an English mathematician made the accusation more explicitly. Leibniz, insulted, demanded satisfaction, and in 1711, he formally appealed to the Royal Society of London to adjudicate. The Royal Society appointed a committee. Newton was president of the Royal Society. He selected the committee. He supplied its evidence. He wrote its report. The report, published in 1713, found decisively for Newton, and Leibniz was left with a verdict handed down by his opponent wearing an institutional hat. And then Newton, anonymously, wrote a long review of the report, praising its impartiality and its conclusions, and had it published in the Society's own journal. That is not a colorful exaggeration. It is documented, and it is one of the ugliest things a great scientist has ever done. Whatever the merits of the priority question, the process was a fraud conducted by the most respected man in European science against a dying rival, in the name of a body founded to establish truth by open inquiry. Leibniz died in Hanover in 1716. He had fallen out of favor at court. His employers had left for London to become the British royal family, and had not taken him. His funeral was attended, according to the accounts we have, by his secretary and almost no one else. The Royal Society did not mark his death. The Berlin Academy he had founded did nothing. The modern verdict is straightforward. Both men invented the calculus independently from different directions, and both deserve the credit. Newton got there first. Leibniz published first and built the better machine. The cost fell on Britain, and it was enormous. British mathematicians, out of loyalty, kept Newton's dots. Continental mathematicians used Leibniz's differentials and integrals, and the Bernoullis and Basel, and then Euler, and then Lagrange and Laplace took that notation and ran with it for 100 years, building analysis into the most powerful subject in mathematics. British mathematics fell behind and stayed behind for a century out of patriotism over punctuation. It was finally broken in the 1810s by a group of Cambridge undergraduates who founded a society dedicated to importing continental methods, and who described their campaign with a pun they were extremely pleased with. They were fighting for the principles of deism against the dot age of the university. One of them was Charles Babbage, who will be back. Now the bishop. George Berkeley was an Anglican clergyman, later Bishop of Cloyne in Ireland, and a philosopher of the first rank, the man who argued that material objects have no existence independent of being perceived. He was also a serious controversialist with a grudge, and in 1734, he published a short book attacking the mathematicians. His motive was not mathematical. It was too colloquial. You too. Berkeley was tired of scientifically minded gentlemen dismissing Christian doctrine as unintelligible mystery, and the book is addressed, pointedly, to an unbelieving mathematician, generally taken to be Edmund Halley. Berkeley's argument was, before you sneer at the mysteries of religion, look at what you believe. You accept, on faith, quantities that are neither something nor nothing. At least our mysteries are honest about being mysteries. That is a debating move. But to make it, he had to actually understand the calculus, and he did better on this particular point than its practitioners. He walks through the derivation exactly as I did above. He observes that in order to divide by the increment, you must suppose it is not zero. He observes that in order to discard the leftover term and obtain an exact answer, you must suppose that it is. And he points out, with some relish, that this is not a subtlety or an approximation, but a plain contradiction. You have used a supposition and then destroyed it, and no amount of rhetoric about quantities being evanescent, vanishing on their way out, repairs it. A quantity that has vanished is zero. A quantity that has not vanished is not negligible. And then he asks what these fluxions actually are. Not finite quantities. Not quantities infinitely small. Not nothing. And he offers his own answer, which is the most famous phrase ever aimed at a mathematical theory. Might we not call them the ghosts of departed quantities? He had one more shot, and it is the cleverest. He argued that the reason calculus produces correct results despite invalid reasoning is that it contains two errors which happen to cancel. That is a genuinely disturbing charge, because if true it means the successes prove nothing. The machine is not working, it is failing twice in opposite directions. Here is the part that matters most, and it is why this chapter closes part 3. Berkeley was right, and nobody could answer him. The English mathematicians who replied, and several serious ones did, produced defenses that were partly evasive and partly geometric. Attempting to recast fluxions in the rigorous Greek style, so that no infinitely small quantities appeared at all. The most substantial of these efforts ran to hundreds of pages, was widely respected, was almost unreadable, and did not solve the conceptual problem so much as tunnel around it. The Annus situation from 1734 until well into the 19th century was this. The most powerful and productive mathematics ever devised rested on an operation nobody could define. Everyone knew it. Some of the greatest analysts of the 18th century wrote uneasy passages about it. And they all kept going because the results were correct and correct in ways so specific and so surprising that no amount of philosophical unease could stand against them. And what results? Newton's Principia in 1687 had used these methods, though he presented the finished arguments in classical geometry, partly for respectability and partly, one suspects, because in that era a proof was still supposed to look like Euclid, to show that a single inverse square law of gravitation accounts for the fall of bodies on Earth, the orbits of the planets, the paths of comets, the tides, and the slow wobble of the Earth's axis. One law derived mathematically, matching everything. Over the next 2 centuries, calculus described the vibration of strings, the flow of heat, the propagation of sound and light, the motion of fluids, the shape of a chain hanging under its own weight, the stresses in a bridge, the behavior of electricity and magnetism. In 1846, astronomers found a new planet by calculating where it must be from irregularities in the orbit of Uranus, pointing a telescope at the spot and finding Neptune within a degree of the prediction. Mathematics located a world nobody had seen. All of it built on the ghosts. I want to draw the lesson out plainly because it contradicts the picture this book set up in Chapter 4 and it needs saying. Euclid's machine suggested that mathematics is a structure erected on declared foundations, where nothing is used until it has been earned. That is what mathematics looks like when it is finished, and it is what makes it uniquely trustworthy. It is not how the subject is made. What actually happens over and over is this. Somebody finds a technique that produces right answers for reasons nobody understands. It gets used because it works. The results accumulate and the successes make it impossible to abandon and impossible to justify. And then, usually generations later, somebody works out what was really going on, rebuilds the foundations underneath the structure that is already standing. And the textbooks are rewritten so that it looks as though it had been done properly all along. Rigor is not the engine of mathematics. Rigor is the cleanup crew. It arrives after the party, and it is essential, and it is not what made the party happen. Berkeley saw a discipline using an operation it could not define. He was right about the diagnosis and wrong about what to conclude. The correct conclusion was not that the calculus was invalid. It was that the calculus was true in a way that had not yet been captured, that the mathematicians had hold of something real and were describing it badly. The answer took 150 years, and it is Chapter 19. The resolution when it came was to stop talking about infinitely small quantities altogether. Instead of asking what the ratio is when the increment becomes 0, you ask what value the ratio approaches as the increment is made smaller and smaller, and then you define approaches so precisely, in terms of ordinary finite numbers, that no ghost is ever invoked. Nothing is ever set to 0. Nothing is ever both something and nothing. The infinitely small vanishes from the theory entirely, and what remains is the concept of a limit, which is unglamorous and airtight. That is the answer to Berkeley, and it took Cauchy and Weierstrass and a good deal of 19th century pain to produce it. But there is a Coda, and it is one of my favorite things in this whole book. In the 1960s, a logician named Abraham Robinson proved that you can have infinitesimals after all. Using tools from mathematical logic that did not exist until the 20th century, he constructed a rigorous extended number system containing genuine infinitely small quantities, not approximations. Not figures of speech, but numbers greater than 0 and smaller than every ordinary positive number, obeying consistent laws, in which the original arguments of Newton and Leibniz go through essentially as written and are perfectly valid. The ghosts got bodies. 230 years after Berkeley asked what they were, the answer turned out to be Exactly what Newton and Leibniz thought they were, and a number system nobody had known how to build, which is the pattern of this entire book in one paragraph. The impossible object is admitted because it works, condemned because it cannot be justified, exiled, and replaced by something safer, and then, long after everyone has stopped caring, vindicated, defined, made rigorous, and handed to students who will never know it was ever a scandal. That is the end of part 3. Look at what 200 years produced. A system of symbols compact enough that a page of reasoning became a line, and structured enough that the symbols did part of the thinking. A general solution to the cubic, and out of it the imaginary numbers, an impossible quantity that turned out to be the language of waves, circuits, and quantum mechanics. The wall between algebra and geometry torn down, so that curves became equations, equations became pictures, and space acquired as many dimensions as you cared to give it. The future annexed, chance shown to have laws, uncertainty made calculable, and with it insurance, statistics, and a whole new way of holding beliefs. And finally, the calculus, the machinery of change itself, which took the physical world and made it computable. Every one of these was built on something its builders could not justify. The imaginaries were nonsense that worked. The infinitesimals were ghosts that worked. Even the coordinates rested on treating geometric magnitudes as numbers, which the Greeks had proved you could not simply do. Europe in these 2 centuries made a bargain. Results now, foundations later. It was, on the evidence, right bargain. It also could not last because the structure kept growing and the ground underneath it was never checked. And by the beginning of the 19th century, mathematicians were producing results that contradicted each other. Series that summed to different values depending on how you added them. Functions that behaved in ways that ought to have been impossible. Arguments from geometry that turned out to depend on assumptions nobody had noticed making. Part 4 is the reckoning. It is the story of a subject that stopped, went back to the bottom, and asked what it had actually been doing for 200 years, and of what it found down there, which was very much worse and very much more interesting than anyone expected. It opens with the most prolific mathematician who has ever lived, who wrote more than anyone before or since, went blind, and did not slow down.